right, we had a big introductory video. We just covered concepts. Well, here we're going to get really down in the dirt. Just do a bunch of examples, see what does this actually look like. Let's get some hands-on, hard well, we're not going to worry about applications, but examples of what the derivative looks like in actual numbers and stuff like that, and actual pictures, and not just generalities. So let's do example 1. Example 1 says find the equation, or find an equation of the tangent line to, and part A is going to be to the graph of f of x equals x squared at the point x equals 3. So you might say, what the heck is a tangent line? Well, go back in your notes. The tangent line to a function at some point A, here, that point is 3, is the line passing through that point. Okay, so let's write that down, right? We need the line passing through that point, 3, comma f of 3. Oops. Right. A is 3 here. So it's the line passing through that point with this slope. And there's 2 ways of finding that slope. With slope m subtangent, and there's 2 ways of finding it. 2 ways of finding the tangent line slope. The derivative. The slope of the tangent line is the slope of the function, which is the derivative. Okay, so we need a line that passes through a point with a certain slope. We'll use point-slope form. But first we have to find the point and we have to find the slope. Once we find the slope and the point, we can use point-slope form and get the equation of that tangent line. All right, so I'm going to show you both ways of finding the slope. There's 2 ways. Here's the first one. It says the slope of the tangent line, aka the derivative, is equal to the limit, I'm just copying down the definition, as x approaches A here is 3, right? So it's the limit as x approaches A is 3 here, of f of x minus f of A is 3, divided by x minus A, again, A is 3. Now you might say, all right, this is a rational function. Well, you wouldn't really be right. Oh, actually, you would turn out to be right. Let's use direct substitution. Plug in 3. Well, we can't plug in 3 here. We're going to get 0 divided by 0. So how do we evaluate limits when we have that indeterminate form 0 over 0? We try to simplify and use some tricks. So this is the limit as x approaches 3 of, what is f of x? F of x is x squared. This thing and this thing, they're equal to each other. They are the same thing. So let's replace the f of x with what f of x is. F of x is x squared, so we replace. Minus f of 3. That's the function value at 3. It's going to be 3 squared. And the denominator doesn't change. And again, we can't use direct substitution. We'll get 0 over 0. We have to keep simplifying. This is the limit as x grows to 3 of x squared minus 9 over x minus 3. We're getting closer. We've seen limits like this before. We factored and canceled. This is the limit as x goes to 3. It's hard for me to write at the bottom of this tablet. The top factors to x minus 3, x plus 3. That's the difference of squares. Now, we can't normally cancel unless we know that x is not equal to 3. Because if x is equal to 3, this is undefined. But if x is really close to 3, we can cancel and it's going to be the same. And that's exactly what we have. X is getting really close to 3, but never actually hitting it. So that's going to be equal to the limit as x approaches 3 of just x plus 3. This is a polynomial. We can now use direct substitution. All right. The slope is 6. So we were asked to find the equation of the tangent line. And the tangent line is a line passing through that point with this slope. Well, what is f of 3? We found f of 3. F of 3 was 9. It's a line going through the point 3, 9 with this slope. Let's use point slope form. Y minus y naught is equal to m times x minus x naught. The y value is 9. The slope is 3. The x value, the slope is 6. The x value is 3. This should be the equation of our tangent line. How can we check our answer? Let's graph it. And if we did it right, it's going to look really good. If we did it wrong, well, hopefully you won't see what that looks like. So we're looking at this function, y equals x squared. And specifically, we're looking at this function when x is equal to 3. We're looking at this point right here. Let's plot that point. That's point 3, 9. I want the tangent line. The tangent line at that point. And I said, here's what I think the tangent line is. Y minus 9 equals 6 times x minus 3. Oh! Let's zoom in on that a little bit. Look at that. Look at that. See how this tangent line, this pink line, just skips right across it. That's very normal for tangent lines. So the blue one's curving, and this is a tangent line. It's a line that just bounces right off of it. The slope of the tangent line is the same as the slope of the graph at that point. It's the derivative of the graph at that point. It is equal to 6. Rise over run is 6. We go up 6, right 1. That's how it all ties together. And that's how we can visually see this. Ah. Don't worry, we're going to do some more. I said I'm going to show you 2 different methods. The blue method was the first one, using this formula. We can also find the slope of the tangent line similarly, using the second formula, and the second one's going to be very, very useful in the next section. Let's use the H formula. So we did the blue one. Let's have the next one be green. This is the second method of finding the slope of the tangent line. It's that second formula. It says, instead of thinking about x getting close to a, let's talk about something called h, where h is the distance between those 2 points that we're using on our secant line. Remember, secant line is just a line between 2 points. And as these 2 points get closer and closer together, the slope of the secant line approaches the slope of the tangent line. And that's exactly what we're doing here. So f of a plus h minus f of a all over h. We copied that definition from over here. And now we just plug in everything. This is the limit as h goes to 0. Remember, a was 3. So this becomes 3 plus h. This is still 3. And this is h. And remember that our function is x squared. So again, algebra is, I cannot say this enough, algebra is going to be the hardest part of this entire class. This is function composition. This says, this is my function, and I'm plugging in 3 plus h into this function. If we plug 3 plus h into the squaring function, then instead of x squared, we now have 3 plus h squared. We found f of 3 to equal 9 from earlier. And now we just simplify. Oops. Because again, we can't use direct substitution here. That causes us to divide by 0. So we have to simplify. We FOIL out the top. That'll be 9 plus 6h plus h squared minus another 9. Ooh. Plus a 9 minus a 9. They cancel each other out. That's the limit as h goes to 0 of 6h plus h squared. We still can't use direct substitution, but just like what we did over here, right? We had 0 over 0, and then we factored and canceled. We're going to factor and cancel again. As the limit as h goes to 0, we can only factor out an h here. But as long as there's the same factor in the top and the bottom, we can get cancellation. And you'll see that we get to some place that's really similar to where we were at before. Polynomial, direct substitution works for limits. And again, this is another, oftentimes this is more complicated, another version of finding the slope of that tangent line. But it's going to be, for most things, more useful in the future. But for this section, you can use both methods. Green method, blue method. And it's just depending on which formula you want to use for the slope of that tangent line. Slope of the tangent line is the derivative. It's the slope of the function at that point. And that's basically this video. I'm going to do 2 more examples though, just to really give you guys a lot of examples, a lot of ways to see these calculations. Again, watch out for your algebra. Let's look at the tangent line to this function at this point. So again, slope of the tangent line. Sorry, the tangent line is a line that passes through the point 2, f of 2. F of 2 is the function value at 2. Just plugging in 2. The y value at 2 is going to be 1/2. And again, the slope of that tangent line is the derivative, m sub tangent, that we had those 2 definitions. And again, you can do it in 2 different ways to find m tangent. It's the limit as x approaches a is 2, of f of x minus f of a divided by x minus a. And in fact, this is a really good opportunity for you to pause the video and try to see if you can mimic part A to find the slope of the tangent line in part B. Okay? Pause me. Hopefully you did that. And otherwise, if you're stuck, I will help. So we need to simplify this. So this is the limit as x approaches 2. What is f of x? F of x is 1 over x. And f of 2, we already found that. That's what happens when you plug 2 into our function. And we have our denominator. Now, hopefully you got to this point. And then it's a little bit more complicated to simplify this limit. We can't use direct substitution. We have to simplify. Go back to chapter 2, videos or notes. How do we simplify limits with complex fractions? We get rid of the complex fractions, usually by multiplying by the LCD. So we look at all of the little fractions. This is the denominator of this little fraction. This is the denominator of this little fraction. There is no denominator. There is no little fraction on the bottom. We find the least common multiple of these denominators, which is 2x. LCM, least common multiple, or LCD, least common denominator. Those are maybe some things that you're going to want to review. And then we multiply the top and the bottom by that LCD divided by 1. This whole thing is equal to 1. So we're not changing this function as long as x is not equal to 0. But x is really far away from 0, so we're okay. Now we need to simplify this. So this gets distributed. And what we get is the limit as x approaches 2 of 2x over x minus 2x over 2 divided by 2x times x minus 2. It's usually a good idea to leave things factored in the denominator. And that's a good rule of thumb for any simplifying of rational expressions. Anytime you're simplifying fractions, the denominator is usually best to keep factored. Oftentimes we do multiply out the top though. So, cancellation. Cancellation. We get something really nice. That's why we chose 2x. That's why we chose the LCD. We'll always get those little fractions to cancel. There's a limit as x approaches 2 of just 2 minus x over 2x times x minus 2. Again, we finished the calculus of this problem. Calculus was over right here. Everything after this, all the hard stuff, that's algebra. So the calculus isn't hard compared to the algebra, in my opinion, and in a lot of my previous students' opinions too. So we'd like to cancel this, but this is not the same as that. They're very similar, but they're not the same. Oh, crap. I randomly have this circle. I don't want this circle anymore. All right, so in order to make them the same, we factor out a negative 1 from that numerator. The limit as x approaches 2 of negative x minus 2 over 2x times x minus 2. Well, why can we do that? If we distribute that, we get negative x plus 2. Negative x plus 2 is exactly what we had. Plus 2 minus x plus 2. That's the same thing. And now we can cancel these. And we're left with the limit as x approaches 2 of negative 1 divided by 2x. Now this is rational. We're not dividing by 0. We can use direct substitution and get negative 1/4. That's our limit. All right, and all that's left is using point slope form. Y minus the y value, which was 1/2, equals the slope, which we found was negative 1/4. Right, that's the slope of the tangent line, aka the derivative, times x minus the x coordinate, which was 2. And if we graph this, we should get a nice tangent line. And let's see if we do. Maybe I messed up. It definitely happens. Hasn't happened too much in this class, but it definitely happens. So we're looking at 1 over x, this reciprocal function at x equals 2. So we're looking right here. We're hoping that we get a tangent line right here. Keep your eye on this point. That's the point 2, 1/2. Keep an eye on that orange point as I type in the formula for our tangent line. Y minus 1/2. Don't hold your breath. No, maybe hold your breath. No, don't do that. Y minus 1/2 equals our slope, negative 1/4, times x minus 2. Oh, there it is. Look at that tangent line. See, it gets really close to the blue function, then skips off of it and keeps on going. That's what a tangent line looks like. The slope of this pink tangent line is the slope of the function. It's the derivative. The slope of the tangent line is what happens when you look at slope of secant lines and get those 2 points really, really close to each other. Right? As you have 2 points, this is our secant line, and the 2 points get really, really close to each other, it approaches the tangent line. Secant line, tangent line. That's the relationship. That's what derivatives are all about. All right. Again, we've already introduced all the new stuff for this video. We're just doing extra practice. So let's use that second formula, the formula with the h. We already finished this problem. We already finished part B. I just want to show you another way of finding this slope, just using a different formula. It's that second formula with h in it. So limit as h goes to 0 of f of a plus h minus f of a all over h. And again, we said a was 2. We said f of a was 1/2. We said f of x. These are all the things that we already had. I'm just writing them down here so we can put them all together. There's the limit as h goes to 0. We need to plug in a. A is 2, right? 2 plus h. Plug that in. That gives us 2 plus h squared. Right? F is the squaring function. F of x is the rule, the function that says anything you give me, the output is going to get squared. So I'm giving you a 2 plus h. The output is that thing, 2 plus h squared. It's going to be 2 plus h squared minus f of a. We said f of a was 1/2. All divided by h. We can't use direct substitution. Wait, sorry. X squared, that was the function from the last, from part A. Our function here is 1 over x. So this will be 1 over 2 plus h. Whew. I was like, this is looking weird. It's looking weird because you're using the wrong function. And our problem solving strategy is going to be the same as before. We have a complex fraction. To eliminate the complex fraction, we multiply by the LCD of the little fractions. What's the least common multiple of 2 plus h? And 2. That's a little bit harder of a problem than we did before, but it's going to be 2 times 2 plus h. And we multiply it all through. When we do that, we get the limit as h goes to 0 of 2 times 2 plus h divided by 2 plus h minus 1 times 2 plus h over 2, all divided by h times 2 plus h. All the numerators in the little fractions get that 2 times 2 plus h. All the numerators get this. And then just like before, things are going to cancel. Things should always cancel. Whenever we use this method, the little fraction should always go away. We're left with 2 minus 2 plus h. Don't forget those parentheses. We have this. Again, this is hard algebra. This is hard algebra. I do not disagree. I'm going to do a mistake. Why is this wrong? Why is it wrong to cancel these 2 plus h's? And the answer is, when you have a rational expression, when you have fractions, you can only cancel if they have common factors. And the bottom is factored, but the top is not factored. We need to simplify the top before we can do any cancellation. That's going to be the limit as h goes to 0. Distribute that negative, we get 2 minus h. And we still have to simplify further. But at least now the top has something nice. We have a plus 2 minus a 2. So the top actually is simplifying to something nicer. The top is just a negative h. And now the top is fully factored. The bottom's fully factored, so we can cancel. The top becomes negative 1. The bottom is 2 times 2 plus h. We can now use direct substitution. Plug in h equals 0. Should get negative 4th. And I'm hoping that negative 4th is what we had using the blue formula as well. So again, a lot of times, the second method, this green formula, is going to be messier algebra. But it's going to be more useful in the future. So it's good practice. But for this section, for 3.1, blue, green, use either one. Okay? Let's do one final example to finish off this video. Example 2. Find f prime of 2 for f of x equals 3x squared minus 4x plus 1. Remember, f prime at a point, what did that mean? f prime of a is the slope of the tangent line there. It's the derivative. So f prime at a just means use one of these formulas to find the derivative or slope at those points. Okay? So here, our a value is 2. We also are going to need to know f of a, so we just plug 2 into this function. It's going to be 3 times 2 squared minus 4 times 2 plus 1, which is going to be 12, minus 8 plus 1, which should be 5. So a is 2, f of a is 5, and we can use either formula. Let's use the blue formula. F prime at 2 is the same as the slope of the tangent line at 2, which is the limit as x approaches 2 of the slope of that secant line. F of x minus f of a divided by x minus a, and a is 2. It becomes f of x is 3x squared minus 4x plus 1 minus f of a, we said was 5, divided by x minus a, which is 2, and we just simplify. The limit as x approaches 2 of 3x squared minus 4x minus 4 divided by x minus 2. This looks a little weird. Hope I didn't make a mistake. We'd like to factor the numerator, and hopefully the numerator has a factor of x minus 2 so we can cancel. All right. So we're going to try to factor. The AC method works, or you can use a guess and check method. The guess and check method actually is really, really nice here because we know what we kind of want. We want a factor of x minus 2, so we're hoping we're going to use that in our guess and check method. So this has to be a 3x. That's the only way to get 3x squared. And this has to be 2, and it has to be a positive 2, because that gives us a minus 4. So let's check our answer, make sure this is good. This gives us a plus 2x and a minus 6x for the middle term. Plus 2x minus 6x. Good, that's minus 4x. And if we do make a mistake, the graph at the end, checking our work with Desmos, will let us know as well. So as long as x is not equal to 2, these two things cancel. X is getting really close to 2, but never touching it. And we're going to get that the derivative is equal to 8. We can now use direct substitution because we have a polynomial, specifically a line. The slope of the tangent line is 8. And again, we can check our answer. This one only asked for the derivative. It didn't want the slope of the tangent. It didn't want the whole tangent line. But we can easily graph the tangent line if we want. This is the function y equals 3x squared minus 4x plus 1. We're looking at the point 2. Whoa. We're looking at the point 2, 5. As a side note, it's really important that this point is on the graph. If this point is not on the graph, then we found the y value wrong. And then we found that the equation of the tangent line is y minus the y coordinate equals the slope, which we found was 8, times x minus the x coordinate, which is 2. Ah! Beautiful. It takes like 15 seconds to check this on Desmos. And it's a really good idea because it also gives you a visualization for what derivatives are all about. Derivative is the slope. Slope of the tangent line is the slope of the function. The tangent line is what happens when our secant line, when those 2 points that form a secant line get really close together. That's kind of how all the topics here are related. Ask questions. If something on this video doesn't make sense, send me a message on Canvas, send me an email. Say, Jason, I was watching the video 3.1.2, and at 8 minutes into the video, you said this. I don't get why that's true. These are things that you can ask me. All right. Have a good day, and bye-bye.